Hello, welcome to the tutorial on generalized linear models in R. I demonstrate you how to implement a GLM model in R. First of all, the first thing you always do is to set a working directory. So here you have to, in the first lines, you have to enter your file path where you want to work in. We have done this a couple of times before and you should be familiar with that, so I don't go into details anymore on this aspect. Our demonstration code comes from an example from the book of Main Donald 2010, and the research question is which environmental variables are most relevant to explain the occurrence of the southern corroboree frog. This is a species that is critically endangered, and several environmental variables have been investigated in an area I think in the Blue Mountains in Southeast Australia. And the question is which environmental variables predict the occurrence or explain the occurrence of this frog. So if you want to tailor or develop conservation strategies, you need to know which variables are important for this frog. So we load the frog data first, and in fact we do a multiple regression in the GLM. So you may be familiar with the multiple regression analysis that we did in the previous session, and we translate this here to the GLM case. So we load the library which contains the data, that's the DAG library, and have a look at the data. You can have a look more detailed on yourself which variables are contained, and here's also a link or a reference to the thesis from which this data originates. So have a look yourself for more details on the environmental variables. Why don't we do just a linear model? Well, let's have a first look. We just take one of the variables and fit these against the presence and absence of the species. So it's basically the species can either be present or absent. Now we've just fit a linear model. We have learned this, you have learned this, how to do this before. We look at the summary, and the summary function tells us, or the model function here, that we explain about 10% of variation, which is not a lot, but for a single variable in an ecological model, that is not too bad in the ecological context, given the many environmental variables that influence the occurrence of species. But when we look now at model diagnosis plots, we see that there is something severely going wrong. So have a look at the QQ plot of the standardized residuals against the theoretical quantiles from a normal distribution. We see that there is a very odd pattern here. The same holds for the residual versus fitted plot. So that's clearly a case where we know that the linear model cannot be fitted like we did, that there are really problems here. And the reason is obviously that we have presence-absence data, so zeros or ones in our data set, and this is clearly not normally distributed. So for these cases, as we have discussed in the lecture, we should use the generalized linear model. And the first thing we do is we look at the data. So the data analysis strategy is the same as introduced previously. So we first inspect the data. We use the package car for that. Show you a different function to what we used in the linear regression modeling context. And we just plot the environmental variables. So have a look yourself in the data set what the columns 4 to 10 code for and which variables we display. So this is the resulting plot. First we can look at the distribution of data points for the different variables, and we see that for most of the variables we have a relatively balanced and relatively normally distributed data set, although for the couple of variables like distance, number of pools there, and number of sites, there is a little bit of skewness of the data. If we look at the relationships between data, we see also that some variables like mean, min, so that's the precipitation minimum and precipitation maximum, or the temperature, have a look yourself in the variables, that they are strongly correlated. So also with average rain, there's a very strong correlation. However, we look first at the data sets, whether we transform some of the variables. When we look at the spread of the data, then we see that the distance spans about 2 orders of magnitude. The same holds for the number of pools, whereas the number of sites is rather narrowly distributed. So we decide that we check whether we should square root or log transform the two variables with the wider spread of values, which is the distance and number of pools variable. Let's have a quick look. So we use this function here. We just plot in one window the distance and number of pools. On the one hand, we plot just the density. In the second line, we plot density for the square root transformed data, and then for the log y plus 1 transformed data. Clearly, you have to do this because in many circumstances, if you have, for example, zeros in the data set, this would return an error otherwise. Let's quickly check. And we see that, in fact, the distance and the number of pools look relatively more balanced and are not skewed anymore when we use a log transformation. So we log transform the data. In this case, we don't need a plus 1 because the minimum number is 1. And we log transform the number of pools and distance and add them to the data set. So the next step of our analysis is to look into collinearity. We've already seen that collinearity may be an issue here, and we check again. So here we have to modify now our selected columns because we have added 2 columns 11 and 12, the log transformed number of pools and log distance, and of course we should look at the correlation structure with them and not at the untransformed variables. And what we see is that we have high correlations between altitude and the mean, min, and min, max. With average rain, there's also some correlation structure, whereas the other variables show no obvious pattern that should worry us. If we calculate the correlation coefficients, we see confirmed what we already expected, that the correlation is almost 1 for altitude with the mean minimum temperature and the mean maximum temperature. We can also calculate the variance inflation factor. So we do this. You've learned before how to do this for the linear model in the previous session. For the linear model, the syntax was very similar. So there's a lot of syntax here that doesn't need thorough explanation. instead of calling the LM function, we just call the GLM function. So that's pretty easy to remember. Then we have the formula notation, the formula syntax. So that's the same as for the LM. Something novel that you see here is the argument family equals binomial. Then a bracket opens and you put the link function there. And that's actually an argument that is specific for the GLM. So you have different types of error distributions, the binomial, the Gaussian, or the Poisson distribution, and you can employ different link functions. And as outlined in the lecture, you could combine them in different ways. And then we have to provide our data set, and that's all that we need for fitting of this model. So we fit the model, and with the fitted model, as you know from the linear modeling, we can now calculate variance inflation factors. So we do this, and we see that we have a really high variance inflation factors for altitude, mean min, mean max, average rain. So if you remember, we had a threshold where people discuss whether threshold should be 4 or 5, or maybe even some are more liberal and say 10. But here this is clearly all over the top. These variance inflation factors clearly indicate to you that something needs to be done here. So just from some ecological reflection, we could argue, well, altitude is probably, in the case of frogs, not itself a determinant of where the frogs occur. It is rather the environmental variables that are linked to altitude, and this would be the mean minimum and mean maximum temperature. So we omit altitude from the model and fit the model again. So I just copy and pasted here the whole code from above and removed the altitude. What I did as well was I have this bracket here with mean max plus mean min. We saw that these both variables are also highly correlated, so contain a little bit of similar information. Well, if you don't want to remove just randomly or arbitrarily rather one of the variables, one trick to keep the information from both variables is to calculate the mean of the variables, but you can also just sum these variables up or subtract the variables. There are different possibilities depending on what you think may be more important. So in our case, we just we just add up the variables and introduce them and use these in the model. And you know that, and you already know that if you just put plus in the formula notation, and this just means add the variable, if you put this capital Y, capital I, and bracket open, bracket close on two variables, then this means they are summed up before they enter the model. So if you need to do some calculations before entering variables in the model, this can be done as shown here. So we fit again and call the variance inflation factor, and what we see is indeed that now all our values are below the threshold of 4 or 5, depending on the one you stick to. So there is not much to worry anymore. We can now safely go on with the modeling. And with the modeling, we do it basically the same as for the linear modeling. So we first compute all possible models. I explained you the advantages and disadvantages of using this technique before, so I don't go into details here. This is just to demonstrate to you how this can be done in R. So we compute all possible models and later on select a couple of models for model averaging. So this code provides us with all possible models. We just call them, and you see that we have here now a set of models, the different coefficients of the models, and the corrected AIC, the difference in the AIC between the best model and the models that are ranked below this one. So you see that except for one variable, all other variables are included here. For model averaging, here because we see that the lowest delta is 2.11, which would mean if we just average models that have a delta lower than 2, then we have just one model. So just for purpose of demonstration, we set the delta here to 3. But apart from that, note that this threshold is of course quite arbitrary anyway. So we get all models within delta of 3 of the archaic information criterion, of the lowest archaic information criterion. And then, as shown previously for the linear model, we calculate the average model, and this is return. We see that number of sites is the variable that is not statistically significant. We see that this is only included in one of the two models, in the model, basically in the model with the lower fit. So this is the modeling of all possible models and multi-model averaging. Another procedure that we discussed before is hypothesis testing that can be used in model selection with all its drawback that we have already also discussed before. So if you would look at coefficients of the model, this is our starting model. By the way, we have a relatively large data set. Let's just before we interpret this, let's look at the data set itself. It is of course the fitted model. We have to look at the number of rows in the data sets. We have 212 observations for approximately 4 or 5 variables that we now have, so we are really good in terms of the number of observations. So the parameters to sample size ratio is ideally in this case, so we have more than sufficient number available here. So we could base our inference, call the summary function again. So we see here the call that we made, the deviance of the residuals. You know that we call the deviation, that we call this deviance residuals, the deviance for the deviance we have in the case of GLM. And we have the coefficients with an estimate standard error. And here the set value. And this set test is similar to the t-test in the linear models. The interpretation is identical, and we see that except for the variable number of sites, all are significantly different from 0. So for the number of sites, this is not given, so we remove this variable from the model. And when we do this, so we can just use the update function, remove the variable, fit the model again, and now we see that all variables are statistically significant in the wild set test. So we would stay, or this would be our final model. Another opportunity for testing is the likelihood ratio test, where you look at the test statistics for the likelihood that are divided between two models. And this is easily executed by the ANOVA function, where you should select the test chi-square because you assume a chi-square distribution of the likelihood ratios. When we do this, we obtain the result that that both models are not statistically significant. That means we can keep the model with fewer parameters. And in our case, this is very obvious, and so both of the hypothesis testing procedures would result in the same model here. We could simplify the model much more, and you could do this just for practicing. You would see that if we removed another variable from the model and conduct a test for the likelihood ratio, that this would be significant. That means we have a significant reduction in the explained deviance. If you just run an ANOVA for a single model, as is done here, then you obtain the results for the sequential reduction in deviance when the terms are added sequentially. Sequentially means that you first enter the log distance, then log number of pools, and so on. This is not really helpful, this type of function. Just show this to you, this type 1 ANOVA, where you add the terms sequentially into the model and check the significance of the reduction deviance is not helpful because it clearly depends on the order in which, on the sequence in which the terms are added to the model. And we see this here if we just choose a different order of the terms in the model and fit the model again. So we have just changed the sequence and run this test again, then suddenly all of the terms in the model are statistically significant. So this is not really helpful for our purposes. If you want to run an ANOVA, then rather use the type 2 ANOVA, the so-called type 2 ANOVA. This type of type 2 ANOVA gives us an indication. It tests whether the removal of any of the terms from the model results in a statistically significant difference in the deviance of the model. This is actually equivalent with the drop1 function, which tests also whether we have a significant reduction. So we see the results are here identical. So you see the p-values and everything is identical. It's just a different wrapper that calls the same function. Okay, as we discussed before, we could also use the archaic information criterion or the Bayesian information criterion. Remember that if you want to be more strict regarding the variables that can enter the model, then rather use the BIC. We do this here, calculate the AIC. We see also compared to the second model that the reduced model with one variable less has a lower AIC, and the same holds for the BIC, where the reduction is actually much stronger, so we reduce 5 points compared to the full model. So irrespective here of our chosen goodness of fit measure, any measure would indicate that we should remove number of sites from the model. Now I want to show you automatic model building, something that we employed before. Again, I'm not going into the details of the problems you may face when using automatic model building. I just show you how it's implemented in R. So first we have to set the full model, Now we have set the full model above. We only need to specify the null model here. So the null model means the model without any variable, only the intercept term. So that would be a global mean for the data, and that is modeled, as we discussed in the other session before, by the response variable tilde 1. And this means that only this mean would be contained in the model. So we calculate the sample size as well for computation of the BIC with the step function, and then rerun the step function. So I explained to you the step function already in the last tutorial on multiple linear regression modeling. You see here that the direction both means the model, or during the model algorithm, it's checked for every variable whether removal or inclusion does prove model fit, and model fit is identified here as BIC. The BIC, we have to specify k equal log n, because this is the parameter that you use for multiplication with the panel determine BIC. Have a look in the last session on multiple linear regression analysis if this is somehow difficult for you to understand where this comes from. So we run the model, and the output, the result, is the same as for the other techniques before. Number of sites is removed to decrease the BIC, and it's just stated AIC here, but this would be the BIC given our parameterization of the function, and the best fitting model contains log distance, log number of pools, average rain, and the mean max, mean min variable. Yes, as we discussed before, the coefficients in these models that we have fitted so far cannot be trusted, and one way is to use post-selection shrinkage of regression coefficients, and this is what we will do now. It's actually, as I discussed before, relatively easy. You just need to run the GLM instead of the LM function, and you have to specify the family that is used in the GLM. So we fit the model. In fact, we have to refit it because the shrinkage function requires some more information than other functions that is provided via x equals true and y equals true. So then we conduct the shrinkage, the global shrinkage. If you look at the results, we see that our shrinkage factor is 0.877, so that has been employed to reduce our regression coefficients via jackknifing. We would obtain the same results as shown here if you would just multiply the coefficients of the model with the shrinkage factors. And then we can also employ parameterwise shrinkage. We've discussed this before, that this should be the method of choice if you decide to first fit the model and then rather use post-selection shrinkage instead of using shrinkage methods directly, as we discussed before, like the LASSO. And if you do this, you obtain these results for the shrunk factors. If we compare this to the global change in the factors, then we have to see, then we see that several variables are quite lower. Several coefficients are much lower than those for the original model. Final step is now to employ shrinkage with the LASSO. And for this we load the library that contains the functions that we need for that, and we fit the model. So we use to specify columns that we want to keep in the data set, we query all names of the frogs columns, so all variables that are contained, and then we select these four for inclusion in the LASSO modeling. We execute the code. The code is very similar generally to the one we used before, and then we unify, or we sum up the both variables as we discussed before. And finally, this is the main line to run the LASSO. So we specify, and that is important, certain R functions require certain input objects, and for example this function GLMnet requires a matrix object. So we could not just enter here a data frame or individual data, and we fit this model. And then we plot the results. So as you know before, the model results display to you the change in the regression coefficients here for the different variables. Variables are just indicated by numbers. You need to know the different variables in the data set to interpret this number. So for example, if we look into the data set, you would know that number of sites is variable 1. We see here that this is more or less shrunk directly to 0 for the whole range of lambda values that we could take. We see that the second variable, average rain, is for large lambda also removed from the model, and log number of pools, the log distance and mean min max is reduced later on. From this plot you would also, so with an increasing lambda, an increasing penalty term, we see that there's actually later on even a slight increase in the relevance of the variable log distance. Can extract coefficients for the different models that are shown here with the coef function. And now we should determine the optimal lambda based on cross-validation. We've discussed this before, what this means. So we run the cross-validation function for the matrix in the data matrix for the response variable of presence of absence, and here we specify the family again. It's a binomial distributed data. Then we plot again. And what we see is that here we have the lowest lambda, so with 4 variables after removal of number of sites. But we could also take another lambda that is within one standard error of the lowest, of the minimum lambdas, but it wouldn't change much. The parameters would be more strongly decreased, more strongly shrunk compared to the original model, but we wouldn't remove another variable. So we can be relatively sure that those variables that we have still in the data set are relevant. So we check at the lambdas as discussed before, and we can then extract the coefficients for different lambdas. So, and we end with the GLM model diagnostics. You know that model diagnostics should be follow-up to any modeling. First, check the dispersion of the model, and this can be done just by doing the arithmetics in your head, by dividing the residual deviance by the degrees of freedom. And we discussed before that this ratio should be approximately 1. And we see here that this is a very ideal. It's indeed the residual deviance divided by the degrees of freedom is really approximately 1. If we had a value returned larger than 2 or smaller than 0.5, then we would speak of over or under dispersion. So the formal calculation can be done like that, and is indeed 1.003, so more or less 1. Now let's look at the QQ plot. What we see here is that we remember the plot that we had in the beginning of the session, and in fact we don't expect for GLM that the QQ plot looks as good as for a normal linear model, but we can still see that we have here at least a monotone relationship. It's not decreasing, it's constantly increasing, and this standardized deviance residuals against the theoretical quantiles looks appropriate. So we draw the residual, person residuals for the different variables, and we should not see here any pattern as well for the different variables, and this is indeed the case. We see here clearly that the linear predictor and the different variables more or less have just a mean of 0 and there's no indication of a clean bias. So then we check for the linearity, this component and residual plots. We see on the one hand, you see an idealized straight line, and in green a smoother line, and we see that both match relatively well, so we can also conclude that we have indeed here a rather linear relationship. And of course, outlier checking for influential points is always important. And again, this is the same as in the case of the simple linear model. You have here the Cook's distance and here the head values. Remember that points are particularly problematic if they have a large Cook's distance and large head values. But here this is not really the case, so we shouldn't worry too much about any of the points. So here you see how you can plot the Cook's distance in a more traditional way that we have used before. We see that we have here one value with a high head value, so a high leverage, but it's not deviating strongly from the main model, so there is no need to worry about. Similar information is provided by this influence plot, where the Cook's distance is indicated by an increasing bubble. And we could also look at values numerically for different meanings of the influence here. Finally, if you decided, and this is not important for us here, but if you decided to remove some of the variables, you could easily do this again also with the update function. I just show you an example here. Let's say you update the frog GLM data set, then you could say, well, this is the subset that we want to remove. If you just keep a specific subset, then you would give the rows that you keep. That would be very unusual. You typically would indicate which of the lines should be removed, and this is done here. So we removed lines 71, the case is 71, 75, and so on. If we execute this, we have here comparison of the first set, that's the original fitted model, and the second is the model where we have removed the points that we have provided. And we see that there are slight changes in the regression coefficients. Instead of the log number of pools, we actually have an increase in the regression coefficient. So our model fits the data better if we remove this outlying data. This actually means that we have a much better fit to the data. But if our next data set, unless we are really convinced that such deviating points are real outliers and should not be considered, then this leads actually to much over optimism regarding our model fit and the large coefficients. So if you would do this, then you clearly need to shrink the data again afterwards. And if you use the LASSO, you actually need to rerun the LASSO simulation, the LASSO algorithm. So again, we plot for the plot here the relationship, how the log distance changes the response variables. That's the partial change after accounting for all the other variables, keeping them constant. And what we see here is that we have approximately a change in the response from -2 to +1. And the biggest change you have across the average range and the mean max against the mean max, mean min function. So you could generally conclude this shows you how to interpret the response. So what is actually the partial value on the axis is a little bit difficult to interpret. So we do this. We have a package called library, and if we use the ilogit function for -2 means we have a probability of 0.1. So that means if it's 10% chance, the probability is 0.1 that a frog is occurring. The inverse logit function, so these are the logit values, for 4 means that we have a 98% chance of, or not chance, but a 98% of the cases the frog occurs. That's what we model here. So we could basically say that the log distance only has a little lower influence for the given gradient that we have compared to the average rain, where we have the full turnover for average rain of 100 millimeters to 200. We see that we have a full response from 0 for more or less no chance of having the frog occurring, compared to high certainty that the frog occurs. occurs. And that fits approximately with our values here. We see that the maximum occurrence and the minimum occurrence are relatively similar to the iLogit values that we chose here for -2 and -4. Why is it extending for average rain above 4, so has a higher probability than we observed in reality? Well, this is because we have additional variables that may decrease this probability of success of having the frog occurring. And then finally we do some cross-validation that can be done here for this function with the CV binary. Again, if we would use a model where we have a check of the prediction accuracy included, implemented as the LASSO, we don't need to do this. In case you don't choose the LASSO, then you can do this here. We have a tenfold cross-validation, and we see that we have a slight drop in the estimate of prediction accuracy. That's actually a rather negligible decrease. And it's clear here that this decrease is not very low because our model is already relatively well fit because we have such a large data set. Okay, that's it for the demonstration. If you want to look into further diagnostics, then I refer you to the books of Logan, Donald, and Fox and Weisberger. And in the next exercise, you should evaluate which environmental variables are the most important for the occurrence of the predipus. You can load the data set here. The data set is provided. If you want to know a little bit more about the environmental variables, which I recommend, then please go on visit this website. After you load the data, you should check the data, and since one of the variables should be a factor, we here run this. Please run this code before you do the modeling. So what should you do? You should run a similar analysis like we did here for the presence absence of the Corybori frog for the predipus, and evaluate and find out the most important environmental variables for this predipus. Should also consider collinearity between variables and so on, and with the model diagnosis and analysis. Okay, thank you very much for your attention. I hope you enjoyed and you learned a little bit during this demonstration, and looking forward to have you listening or watching one of our other videos.